Welcome to my humble channel. Today is a good day for a phoenix rising, in this case something interesting coming out of the dullest of subjects, relative density. First, I would like to thank those of you who have taken the time to watch my efforts, and particularly those who subscribe. I can't really answer why I've made this video. I'm not qualified in math or geometry, except for two things. I am curious, but I don't make stuff up. I discover, I don't fabricate. And every time I discover something, it's a shot of adrenaline. That makes me want to share the good news. The other thing is that nature is far more adept in math and geometry than I ever will be. I don't have to be an expert. I just need to observe with a careful eye. But back to the subject. For background, there are misinformed people who don't believe gravity is observable as a force, and that density somehow creates a tendency for stuff to fall down. Lunacy. Yet there are interesting facets to almost anything. I found something of such tangled nature I was unable to find a solution without resorting to techniques at play, and I am not joking, in quantum computing. I hope I'm not in trouble for what I've done. I happen to have unsupervised access to the largest, biggest, baddest, most comprehensive quantum computational system ever. I don't really know who to ask about using it, and I found a moment when nobody was paying attention. I'll leave it to you to judge my actions. Never use computational resources without authorization. I loaded up the problem I found and read back the results. And now, for as long as I remain unapprehended for theft of computational services, our feature presentation. First, let's get some boring drivel out of the way. Here we have Cousin Eddie's precision lab balance. The ring used for a pivot is some bit of horse tack from the local tractor supply store. The horizontal beam is a shout-out to people who think rockets don't work. It's a launch rod from an Estes model rocket. The black lines supporting the beam are pieces of paracord from Walmart. On the left end are 3 fake eggs left over from my first video about buoyancy. On the right is a lead fishing weight. The can of salt you see in the background is a private salute to relative density researchers. We've already got one problem. The less dense fake eggs appear to be heavier than the much more dense lead fishing weight, and it gets worse. This relative density relationship reverses in water. In air, the less dense fake eggs are heavier. In water, the lead is heavier. Of course, the answer is the golf balls displace more water than the lead. Everything retains its full weight. In concert with buoyant forces, the lighter lead is able to lift the heavier golf balls in water. Boring. It's just as exciting to discover 2 pounds of styrofoam is heavier than 1 pound of lead. But there is something to see here that's just plain fascinating. If I put unequal weights at 3 and 9 o'clock on a wheel left free to rotate, the heavier weight will go all the way down to 6 o'clock. It doesn't matter the relationship of the weights. If 2 unequal weights are on opposite ends of a diameter on a wheel, the wheel will always find equilibrium with the heavier weight straight down, whether the larger weight is 1% heavier or 10,000% heavier. But old-timey 2-pan balances, like an Old West assayer would have used, just tip a little toward the heavier weight. How in the world does that happen? I Googled, but I couldn't find anything. The answer is what a physicist calls moment, or twisting effort. Here's our rocket rod balance modeled in a geometry tool called GeoGebra. GeoGebra is free and open source, a little quirky, but highly useful. We're going to consider an initial state where the balance beam, the rocket rod, is horizontal. The droop is the angle each support line creates between horizontal and the end of the balance beam. Here's a droop of 0 degrees. Here's 25. And here's 45. Rotation to equilibrium will be measured from the initial state. The length of the balance beam can be determined a couple of ways. We can measure it, or we can just hit the cosine button on our calculators. The length of the beam is twice the cosine of the droop angle times the radius of the implied circle. Here's our rocket rod balance mapped onto a wheel. The unequal weights apply moment in opposite directions, fight it out, and settle at some point of equilibrium. Once I saw this, I thought I was home free. Easy deal. Find net moment 0 and declare victory. But there's a problem. There's always a problem. Moment is created with two things. First, there's a moment arm. You could think of the moment arm as analogous to the length of the torque wrench you use on your dirt bike's head bolts. If you don't have a dirt bike, you really should consider one, because that will make it much easier to justify investing in torque wrenches and learning physics. The other part of moment is force applied at 90 degrees to the free end of the arm. Here's what the forces acting on our rocket rod balance wheel actually look like. And here is where my dreams of an easy solution were dashed. The problem is, as you rotate the wheel, two things happen. Each moment arm changes length, and the total length of the moment arms changes as well. The relationship between how many degrees a wheel turns and how much the net moment changes is not linear. Those forces ride curves, not straight lines. First, naturally, my thought turns to those of laziness. At this point, I still wasn't thinking about hijacking time on a quantum computer I don't own. Trig tells us the moment arm on each side is the cosine of the angle between horizontal and the radius extending to the weight on the circumference of the wheel times the weight. Let's set that initial angle of droop to 25 degrees. We shall load weights hanging off points E and F. On the right side, we'll hang a weight of 1.4 units, and off the left, 1.2 units. It doesn't matter what units of weight. The relationship between the two sets where the equilibrium lands. Here's one moment plot drawn in green. It's the cosine of the angle of the weight on the left side times the radius of the wheel and times the weight actually there. That cosine wave is the clockwise moment applied to the wheel. I've set this up so the y-axis intersects the cosine wave at the current state of rotation. Here's the same cosine wave for the other side, drawn purple. Note that it's out of phase and has a different peak value because the weight is different, and because the weight is at a different point on the circle. Those two curvy lines represent the tug-of-war going on. One moment trying to turn the wheel clockwise with a weight of 1.4, the other moment trying to turn the wheel counterclockwise with a weight of 1.2. Here's the sum of the two, drawn in red, to show the net moment on the wheel. When we rotate the wheel enough, the net moment on the wheel becomes 0. Note that when the droop is 0, equilibrium happens with a heavier weight at 6 o'clock. If we set the droop to 25 degrees, we hit net 0 moment at 9 degrees rotation as best we can see. That's nice. We know pretty much the answer, but it's not very satisfying. We need to know the exact answer, and we need to be able to solve for any two wheel weights on any diameter wheel. I puzzled. I agonized. I gave my forehead keyboard-shaped calluses. And then I remembered the biggest, baddest, most comprehensive quantum computation facility ever commissioned. It's right here where I live. I speak, of course, of the cosmos. We live inside the most beautiful, consistent, perfectly operating mechanism imaginable, including all that Newton, Einstein, and many others could envision, and there is still far more to be discovered. The principle of quantum computing I borrowed has to do with how quantum computers find answers. Basically, in a rude and overly simplistic nutshell, they resolve answers by letting natural forces do the work for them. A problem is set up with charges and spins and things I really don't know anything about. The support structure is kicked out of the way, and quantum bits seek their ground state like water flows downhill. You can do the same thing with everyday problems. You can calculate with your grandpappy's slide rule how long it will take a bowling ball to drop from the roof, or you can let nature compute that for you. Drop the bowling ball and read nature's answer with a stopwatch. Either way, you gain the benefit of computation. The universe is, in a real sense, a computational system. Now it's time for nature to do the hard work and solve this puzzle of two weights on a wheel for us. Close your eyes, give it a moment, and let nature spin the wheel to equilibrium. Cool. The hard part's done. All we need to do is read back where it's settled. Notice if we look at this, we see all we need to explain what's going on. It's just icky to solve for exactly what happened. Now let's add the structure of the balance, and let's add a line straight down from the hub intersecting the balance beam somewhere. Note that as the scale wheel rotates, nature tips her hand. When the scale is level, the balance beam is the same length as the moment arms. The proportion of the balance beam is 1-to-1 with the moment arms. When the scale is tilted, the verticals from the ends of the moment arms to the ends of the balance beam peg the beam in proportion to the shifting moment arms. A slope on a graph expresses a proportion. It's rise over run. We can use that. The changing tilt of the balance beam scans all possible moment arm ratios with each spin of the wheel. Nature does a lot of work. With weights of 1.2 and 1.4, we have a total weight of 2.6 units. 1.2 parts out of 2.6 is on one end of the moment arms. 1.4 parts out of 2.6 is on the other. The heavy end has 1.4 parts of the weight and 1.2 parts of the balance beam and of the moment arms. We know the length of the balance beam. 1.2 over 2.6 times the length of the beam gives a length of 0.83659. We know the angle at the circumference is our droop of 25 degrees, and we know the radius. That gives us side angle side, and the law of cosines will tell us the drop from the hub down to the balance beam is 0.42833. We can either use the law of sines or another trip through the law of cosines to find the balance wheel rotated 9.36727 degrees to find equilibrium. Here's a spreadsheet I did to double-check my calculations. As you can see, the left and right beam portions added up to the total length of the beam, and the left and right moments are equal but of opposite sign. Net moment, 0 at just over 9 degrees rotation, which is really nice. We don't have to mess with the real world to know what happened. Wait, you still want to see? Okay, let's give it a go. Spin is a property very important in quantum computing. We're studying rotation. We need a qubit, or quantum bit, fully compatible with spin computation. I have just the thing. Here's my spin-capable qubit. I have weights of 56.17 grams on the left side and 163.83 grams on the right side. These are common fishing weights, and I added my house keys to the right side. Thanks to the predictability of gravity, those weights are uncanny consistent. They might as well be precision lab gear. There are 32 spokes on the wheel for 11.25 degrees per spoke. The droop below horizontal is 2.5 spokes, or 28.125 degrees. To my eye, it's settled with a rotation offset of 4 spokes. Here's the math. The masses on the bicycle wheel weren't concentrated at a single point. There was some distribution of mass along the circumference. The wheel was well balanced but not perfect. My measurement of the wheel diameter was crude. I used a carpenter's tape measure. And there was also radial distribution of the mass. It wasn't concentrated exactly on the surface of the rim, which is what I based my calculations on. In other words, there is some approximation here. Once again, in the spreadsheet, the beam portions add up to the whole length of the beam, and the left and right moments are equal, but opposite, for a net moment of 0 at equilibrium, just what we wanted. The math says I should have seen 42.5 degrees or 3.78 spokes of rotation. Eyeballing it at 4 spokes is a win. And if anyone doubts my bicycle is a quantum computer in disguise, I refer you to 2001: A Space Odyssey. HAL 9000 took an immediate refuge in Bicycle Built for Two when the chips were down. And is it any coincidence HAL sang about a bicycle for two? Two, as in the binary language of automation? I think not. And I think there's something even more fascinating yet to see here, but that will be a topic for another video. I would include it here, but I'm sorry, Dave. I'm afraid I can't do that. Actually, I've discovered I can do that, but this is enough for now. Well, one last comment. None of the math or graphics in this presentation were worked out on paper or with software. As part of this challenge, I imagined a whiteboard every morning when the alarm clock went off and worked everything there. I wouldn't mention it except for a flat earth proponent who called me a senile old I respect his opinion, of course, giving it the full merit it deserves. Besides, if this is senility, may I have some more, please? Live long and prosper. Please click the like and subscribe buttons and join me in future podcasts. Have a great day.